All right, so as we've seen, when we multiply two complex numbers, the modulus multiplies, but the argument adds. And this reminds us of something. There's something else that adds when you multiply. Okay? So if I take two numbers, 2 to the 5th and 2 to the 8th, I get 2 to the 13th. The exponent adds. So what this indicates is that as far as multiplication is concerned, the argument of a complex number behaves like an exponent does, in that on multiplication, the argument adds. All right? When I multiply two complex numbers together, the argument is going to add. So that prompts us to look at cis theta as an exponent. All right, and it turns out that if the base is E and theta is measured in radians, cis theta is simply e to the I theta. There are a number of ways to see this. One way is to see that cis theta times cis theta complex conjugate is equal to cosine squared theta plus sine squared theta, which is 1. E to the I theta times e to the I negative theta. Remember what we said? All we have to do is change the SIGN of theta, right, to get the complex conjugate. This is going to equal e to the I theta minus theta, which is e to the 0 or 1. All right? We can also check and see that the derivative with respect to theta of this equation respects the equation. If I take the derivative with respect to theta of cis theta, I get negative sine theta plus I cosine theta. All right? If I take the derivative with respect to theta of e to the I theta, I get I e to the I theta, which is I cosine theta minus sine theta. All right, so that checks out. The standard way to develop this relationship comes from Taylor series expansions. So if I look at the Taylor series for e to the I theta, so that's going to be 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial I theta to the 4th over 4 factorial, on and on and on. Remember, that was the expansion for e to the x. It was x to the n over n factorial added all the way up. If I square these, if I power these out, what I'll find is that I get a series without i's and a series with i's. And this is the series for cosine, and this is the series for sine. All right? Cosine theta plus I sine theta. That gives us a very interesting relationship, very interesting identity for the sine and the cosine. The cosine of theta is equal to e to the I theta plus e to the minus I theta divided by 2, and the sine of theta is equal to e to the I theta minus e to the minus I theta, all divided by 2I. These will be very important to us for a number of reasons going forward. They can also be used to extend. So right now, we're only writing this for real theta. Okay? However, we can use these expressions to extend the definition of cosine and sine to cover the whole complex plane. Cosine z is equal to e to the iz plus e to the minus iz divided by 2, and sine of z is equal to e to the iz minus e to the minus iz divided by 2I. Here, in general, for arbitrary z, we can ask about cosine squared z plus sine squared z. Cosine squared z plus sine squared z would be equal to e to the iz plus e to the minus iz over 2 squared plus e to the iz minus e to the minus iz over 2I squared, which is clearly equal to 1/4. And then let's see what we've got. We're going to have e to the iz plus e to the minus iz squared. Here I have an I squared, so that's going to be minus e to the iz minus e to the minus iz squared. Clearly, when we square these out, only the cross terms are going to remain. The squared terms are going to cancel out. The cross term here is 2. The cross term here is -2. And so, as expected, we find that cosine squared z plus sine squared z is equal to 1 for all complex numbers z.